The quest of gaining knowledge about our solar system has led to different types of research conducted both in space as well as here on Earth. Planetary exploration is one field that gained interest in recent years as the question arises whether there are habitable planetary bodies or such that have been in the past. For finding answers to this and many more questions, it is crucial to conduct research on the surface of a respective planetary body. Previous missions to the Moon or Mars, for example, included landers or rovers capable of acquiring samples from the surface. In this video, we will discuss robotic sample acquisition. First, we will talk about different types of samples and the two main ideas on how to acquire them. For this, we will need a robotic manipulator, which will briefly be discussed. We will then talk about different end effector tools to acquire the samples as well as some real-world examples. So, let's talk about samples. In general, a sample is a limited quantity of something which is intended to be similar to or represent a larger amount of that thing. This also applies for samples in planetary exploration. On planetary bodies, we find mainly rocks and soil, so those are the physical objects of interest. A handful of missions returned such samples from different planetary bodies as well as from asteroids. During the Apollo program, for example, about 2,200 samples from 6 different landing sites on the Moon were returned to Earth. The astronauts collected various samples using sample bags, scoops, or similar equipment. The samples were then stored on board the lunar module for a subsequent return to Earth. In total, about 380 kilograms of soil and rock samples were returned to Earth by the Apollo program. The Soviets also managed to return samples from the lunar surface with the Lunar 16, 20, and 24 missions. Those three were all stationary landers using a drill to acquire samples. All the missions mentioned had one thing in common. They were mostly stationary and some even remained on the surface for short times, ranging from just a few hours to 3 days. Therefore, the number of samples that could be acquired was limited by the surrounding samples that could be physically reached or by the time on the surface. For missions that would remain on the surface for longer extents, such as rovers, this form of sample acquisition will sooner or later not be feasible anymore. This is due to the storage capacity needed to store and return the samples to Earth. This capacity is typically very limited in terms of volume as well as mass. Acquiring many samples would require frequent sample return missions to not run out of storage capacity. In contrast to taking the sample with us, we can actually do the science right on the surface. This is called in situ analysis and yields data rather than physical samples. It is therefore necessary to carry the scientific instruments needed on board the rover, for example. Apart from that, this might be the favorable approach because it is easier to send data back to Earth than samples. Also, a return of samples to Earth requires complex handling of the samples, including quarantine as well as analysis in so-called biohazard containment facilities to avoid contamination. At the same time, contamination of the sample from the external environment of Earth needs to be avoided to preserve the scientific value of the sample. Before we even get to the point of analyzing the samples, they need to be acquired on the surface of a planetary body. For this, a rover requires a robotic manipulator to reach the samples of interest on the ground. A robotic manipulator is a kinematic chain connecting multiple links through different types of joints. There are a few common joints I want to mention here. A revolute joint is a very basic 1 degree of freedom joint which allows rotations around one axis. This works similar to a door hinge. A cylindrical joint adds a 2nd degree of freedom by allowing translation along the rotational axis. Last but not least is a spherical joint. This joint allows rotations along all 3 axes, thus making it a 3 degrees of freedom joint. When combined in a robotic arm, each joint adds its respective degrees of freedom to the chain. In this way, it is also possible to create and thus replace a spherical joint by combining 3 revolute joints. Spherical joints are very difficult to implement as active joints. In fact, they are often used as passive joints. One example for this is the usage in car suspensions. Modern rovers use mostly revolute joints with electric motors because they are relatively simple to implement compared to other types. A very basic example of a kinematic chain is the human arm, which contains spherical joints at both shoulder and wrist and a revolute joint at the elbow. This gives us 7 degrees of freedom. However, 6 degrees of freedom would be enough to reach an arbitrary position and rotation of the end effector, which, in this example, would be our hand. Additional degrees of freedom are redundant and can be used for collision avoidance. Looking back at the human arm, the additional degree of freedom is actually needed because the wrist, for example, does not allow the full 360 degrees of rotation around every axis. Through the additional degree of freedom, we are then able to perform certain rotations of our hand by using the shoulder, for example. The end effector of a robotic arm in a rover sense can be any tool like a scoop or a grinder, or a scientific instrument like a spectrometer. When using a robotic manipulator on a rover, we face some limits and challenges. First of all, there are certain mass and volume constraints which we have to adhere to by design. Typical rover-mounted systems are generally of low mass at around 1 to 3 kilograms and have to be stored in a compact way to not interfere with rover operations. Therefore, most rovers actually give up 1 degree of freedom by not including a roll degree for the robotic arm. In many cases, this is not needed anyway, so the trade-off might be worth it. Although we said a robotic arm with 6 degrees of freedom is capable of arbitrary position and orientation, it is of course limited to a certain work envelope. The work envelope of a robotic arm depends on 3 main characteristics. First, the range of the joints. As mentioned previously, the human wrist, for example, does not support a full 360 degrees. Of course, the rover can only acquire samples that lie within the work envelope of the robotic arm. If we want to acquire samples that lie outside the work envelope, we need to reposition the rover to do so. Since we are typically far away from Earth, a remote-controlled operation of the rover as well as the robotic arm is not possible. Communication delays can range from just a few seconds for the Moon to around 13 minutes on average for Mars. This requires a semi-autonomous operation of the rover as well as the robotic manipulator. This means that the robotic manipulator itself should operate autonomously, but it is possible that a human operator chooses the relevant samples from Earth through a camera system similar to the pathfinding found on current Mars rovers. Different types of surfaces, even on the same planetary body, require different contact forces in order to acquire a sample. The rover should be able to cope with this as well. Also, we need hand-eye coordination to actually pick the samples we want. We humans would do this by looking at the sample with our eyes and use our depth perception to estimate the distance. The quality of the estimate is also subject to our own experience. The rover now faces 2 problems. First of all, we need to determine the position of the sample of interest. This is typically done using stereo vision. Stereo vision works as follows. The stereo camera on board the rover takes 2 images from different locations at the same time. The images are then aligned in order to get a disparity between both images. The displacement of the same pixel in both images can be used to calculate the distance to the object through triangulation. Let's assume the following setup. Both camera lenses are level and the image planes of both cameras lie on the same plane. The pixel X is then projected onto the pixel XL on the image plane of the left camera. The same happens for pixel XR on the image plane of the right camera. Using the similarities of the triangles, we can then determine the distance to the pixel X using the displacement of the image pixels, the focal length f, and the distance k between both camera lenses. Before being able to use this, the stereo camera has to be calibrated. For this, we can use such calibration boards, for example. Rovers also carry such calibration patterns so that the camera can be recalibrated during the course of the mission. Now we are able to locate a sample on the surface, but this only gives us the position of the sample in camera coordinates. To be able to place the end effector in a position where it can grab or inspect the sample, we need a coordinate transform from the camera frame to the end effector frame. This is not a straightforward transform from one frame to the other, but rather a series of coordinate transforms from the camera frame via the rover body frame through the entire robotic arm to the end effector. The coordinate transform can either be known by design, or we need to perform a so-called hand-eye calibration. The following footage shows the hand-eye coordination performed on the Curiosity rover. This picture shows the mentioned problem. Here we want to inspect this gray sample here on the left. We can determine the position by stereo vision, so we know where the sample is, but only in the camera frame and not in the end effector frame. Thus, we need the respective coordinate transform to determine the position in the end effector frame. There are various tools that can be used as an end effector, of which we will cover a few in the following. A scoop is a very simple tool to acquire soil samples from the surface. It depends on the actual implementation, but in general, this works by pushing or rotating a scoop into the soil to take a sample. The Viking program of NASA consisted of two identical orbiter lander systems which flew to Mars in the 1970s. The mission was planned to conduct research to detect life in the Martian soil if it existed. For this, the soil was taken from the surface using a simple robotic arm. The arm could rotate along both azimuth and elevation axes as well as extend in length. When positioned to the desired azimuth and extended to the desired length, the collector head was lowered to the surface. Upon contact with the surface, the collector head was pushed into the soil by a further extension of the robotic arm. Now the lid closes to secure the sample inside of the collector head. The robotic arm gets elevated and retracts back to the lander body. The different scientific instruments on board the lander had different inlets on top of the lander body through which the soil got dispensed from the collector head. For this, the collector head could rotate by 180 degrees to dispense the soil through a sieve. Another example is the Phoenix Mars lander, which landed on the Martian surface in 2008. The mission was set to evaluate the past or potential future habitability of Mars. Therefore, its desired landing location was near the northern polar region of Mars because water ice was suspected to be present at depths of just a few centimeters below the surface. The lander used a 4-degree of freedom robotic arm. The scoop would rotate into the soil similar to an excavator. Besides acquiring soil samples, it was also possible to dig down to 0.5 meters below the surface. The scoop also implemented a rasp at the back. The rasp was used to acquire icy soil samples by cutting into the soil. Particles then ballistically entered the rear chamber of the scoop. This image taken by the lander shows a trench created by the robotic arm. The light blue regions are indications of frost accumulation. There are other designs such as a clamshell grab, which also allows us to grab rocks. More complex designs include grippers, such as the hand developed by the DLR. However, those things might actually be too complex for the task at hand. Moving over to in situ analysis. On most planetary surfaces, we face the problem that the rocks we want to inspect are typically covered in dust. A corer or grinder can be used to expose a fresh surface for measurements by abrasion. NASA's twin Mars exploration rover Spirit and Opportunity both implemented a grinding tool in the so-called instrument deployment device. The instrument deployment device was the end effector of the 5 degree of freedom robotic arm. The rock abrasion tool had a grinding wheel with 2 diamond teeth, which was pointed towards a surface of interest and then used to remove a thin layer from that surface. The brush wheel then removed remaining dust from the surface. The freshly grinded surface could then be analyzed using the instruments also mounted to the instrument deployment device. The Curiosity rover uses a similar configuration with an instrument suite of 5 devices. An X-ray spectrometer and a camera are used for in situ analysis. Compared to the Mars exploration rovers, Curiosity does not use a grinding wheel. Instead, it uses just a brush wheel to help identify surfaces of interest. If such a surface is found, Curiosity uses its percussion drill to acquire rock samples. The samples can then be stored on board the rover for further analysis. The Curiosity rover also implements a small scoop that can be seen in action here. We have now seen a grinder and a drill that work by rotating sharp teeth, thus using abrasion to drill holes into the surface. An interesting different variant of doing this is by using ultrasonic oscillation to drill into rocks. An ultrasonic oscillation is generated using the inverse piezoelectric effect. The ultrasonic interface, often called horn, then excites a free mass which resonates between the horn and the drill bit. This results in a drill bit being jackhammered into the surface. An interesting takeaway from this method is that the drill bit does not even have to be sharp in order to use it properly. Also, there is no wear. With this, I want to conclude the video. We have talked about different methods on how to acquire samples on a planetary body, as well as the challenges that come with it. The included real-world examples then provided an insight into the actual implementation of sample acquisition.